So today we'll be looking further at discrete random variables, and we're going to look at one of the main features, which is finding the expectation, finding the expected value of a discrete random variable. Let's start with something familiar. If we were to throw a fair die 60 times and we got some outcomes, we would usually go ahead and calculate the mean based on our particular sample, based on our outcomes. And the mean that we calculate, we can use that to make some predictions about what might happen the next time that we throw the die. This is true whether the die is fair or biased. If we thought it was biased and we rolled the dice 100 times and we saw twice as many 5s as 2s, we might then predict that the next time we roll the dice, we're more likely to get a 5 than we are to get a 2. So we calculate the mean, and we often use that to make a prediction. Now in this case, the mean was 3.55. If somebody else had rolled this dice 60 times, they might have got some slightly different frequencies, and the mean they calculated could be different. So different samples are likely to give different means. And we already know that the larger the sample, the more we can rely on its statistics. Now here's something that's interesting. As the sample size increases, the experimental probabilities tend towards the theoretical probabilities. As in, with this dice, if we did it 6,000 times, the proportion of times we got the number 1 is going to be closer to a sixth than it is now. The proportion of times we got the number 2 would be closer to 1/6. It's going to be closer to the theoretical probability. We can just start with the theoretical probability rather than having to take a huge sample. Sometimes we don't even have the sample data, but we do have the probability distribution. We do have the discrete random variable, and we can work with it. So let's go ahead and try and find the expected outcome from our discrete random variable. We're going to multiply each x value with the probability associated with it. So the outcome of 1, I'm going to multiply it by the probability of that outcome, which is 1/6. Outcome of 2 is multiplied by 1/6. 3 is multiplied by 1/6. 4 multiplied by 1/6. 5 multiplied by 1/6. And 6 multiplied by a sixth. And we add those together. This is the expected value of this discrete random variable. The discrete random variable was the score we get when we roll a dice. So the expected score we get when we roll a dice is 3.5. Now the mean we calculated was very close to the 3.5, and other means would also be close to 3.5. But here we've got an exact value for the expectation. We'll look at this later in the course, but the larger the sample size, the closer the calculated mean would have been to 3.5. Now, there is a generalized formula for this. I've said it in words, I've given you an example in numbers. Here's the generalized formula, and I want you to really start to be able to read formulas and what they're asking you to do. Here, we're told that the expected value, the expectation of x, is the sum, this is why we were adding, because we have a summation, of x multiplied by the probability x equals x. So that's why I chose the pairs. I chose 1 and a sixth. I multiplied them. The x value of 1 with the probability 1/6. I then added that on to the next pair, to the next pair, to the next pair. So that's what this formula is asking us to do, to multiply each individual x value with its corresponding probability, and then to sum those values together. So this expectation is the mean value we would expect if we had a large sample size, or if we did the experiment lots of times and then we put all of those scores together. Okay, so on the screen we have 3 discrete random variables. These you should be able to find the expectation of even in your head. Let's take 10 seconds. You can pause the video here and see if you can calculate the expectation. X multiplied by its associated probability, and then we're going to sum those together. 1 times 0.1 plus 2 times 0.6 plus 3 times 0.3. That gets us an expectation of 2.2. 4 times 0.5, we can do that quickly in our heads. That's going to be 2. 8 times 0.25, that's 8 times a quarter. That's also 2. And then 6 times a quarter, that's 1.5. Expectation of x, 5.5. And then this last one, those fractions will come out quite easily. 2.5, 10, and 7.5. Expectation of 20. Okay, so a very important feature of a discrete random variable, and actually this is a property that we'll look at for every distribution that we do, both in straight maths and in further maths. Something I want to point out is that if you pay attention to the distribution you have in front of you, you may be able to spot a shortcut to some of the work you're asked to do. We have 2 symmetrical distributions on the screen. The first one is symmetrical because all of the probabilities are the same as each other and the outcomes are evenly spaced. For that reason, the expectation was right in the middle. The expectation was 3.5. There is another symmetrical distribution. The third green one is a symmetrical distribution. The probabilities are symmetrical, with the half being in the middle and 1/4 being on each side. The outcomes are evenly spread around the middle as well, with 20 being in the middle, 30 being 10 above, and 10 being 10 below. So we have 20 and then 20 plus or minus 10. 2 symmetrical discrete random variables, 2 symmetrical distributions. We know the expectation is just going to be that middle value. You are allowed to just state the expectation if you spot you have a symmetrical distribution. Usually we'll just write by symmetry after we've written down its value. So you could write expectation of x equals 20 by symmetry. In an exam, one student may be spending 3 minutes calculating the expectation, while another has spent 3 seconds because they spotted the symmetry in the distribution. So as always, just make sure you're being vigilant while you're doing your maths. You're actually paying attention to the context and the situation rather than just number crunching. Okay, so let's have a look at this example. We've been given a discrete random variable and we've been told the expectation equals 3. So this often happens. You're told what the expectation is and you need to show how you would get to that answer, or you need to use that result to solve for some other unknowns. What do we know about this distribution? Well, firstly, we know that these probabilities should add up to 1. This is true for every discrete random variable. So that second row should add up to 1. We've been told the expectation equals 3, so we can also form a statement 0.1 plus 2p plus 0.9 plus 4q plus 1 equals 3. And here we have simultaneous equations. We'll just process the simultaneous equations. Let's tidy these up first. 2 equations, either the traditional way or you can type these into your calculator and solve to get the 2 solutions. P equals 0.3, Q equals 0.1. Okay, so that's finding the expectation of x. What if we modified x? Here's a discrete random variable. Here's our x values and our probabilities. Now, it might be the number of times you knock on a door before it opens. It might be the number of times you shoot a basketball into the hoop, or the number of times you kick a football over the crossbar. X is the outcome of that random variable. In that case, 2x would be doubling the outcome of that random variable. So we could actually just make a row for 2x, but the probabilities remain the same. So the spread of probabilities would be the same. A graph of this distribution would be the same, except that the x values are going to change. The x-axis has been scaled. How about x squared? Or similarly, in the top row, we'll square each of the x values while the probabilities remain the same. Now, if you're asked to find the expectation of 2x, we'll use the same process, but make sure we're using the seconds table. The same process, but we've modified the top row. So a bit more formally, the expectation of 2x is the expectation of 2 times x times the probability associated. So 2 times the 1 times the 0.1, plus 2 times the 2 times the 0.4, plus 2 times the 3 times the 0.5. And similarly for x squared. So we'll square each of the x values, multiply them by the associated probability. So this is how you're going to calculate expectations, whether it's for x or a modified version of x. And we're just about finished. But before you move on to some practice questions, let's take a quick look at the specification that's on the screen and exactly what it is that students are expected to be able to show, exactly what the examiners are anticipating that you'll be confident in. While you read through that, I want to quickly remind you that it would be sensible for you to come back here and re-watch this video at a later date. Maybe you're coming back in 2 or 3 weeks, or right before an assessment as a refresher. As you watch through the second time round, because you've done your practice and you've experienced these questions for yourself, you've experienced a bit of problem solving for yourself, a lot of what we go through here should resonate with you so much more. And you get the chance to really embed your understanding of the difficult concepts. That'll be anything that I've flagged with the A-star.